Okay, so as I mentioned, today we want to do a quick discussion of the entire course. I will try and condense the previous 35-36 lectures in 1 hour 20 minutes. So it will be a bit of a challenge, but you will have to be fairly attentive, otherwise you'll miss the flow. We started the course with a lot of applications. I showed a video in the beginning which was completely generated using machine learning tools. We also looked at different kinds of apps which you are currently interacting with, Siri, Google Now, Cortana. We looked at this application for transcript. So given a video, can you create a transcript out of it automatically? We looked at this computer vision based technology which was Amazon Go. You can go to any store, you can just pick up things and you can go. So it seems that the TAs are not there. We can perhaps have 3 people start the attendance in the 3 columns. So we saw a lot of these applications. We saw this Google Duplex like system. The important thing across all of these applications which we were discussing was that these are complete systems. Machine learning is a part of these systems, but machine learning is not the entire system. So therefore, whenever we're building machine learning solutions, we should not forget about the whole system as such. We also discussed some challenges which you may face. For example, for self-driving cars, if a car has these stickers attached, your automated system will likely fail, whereas a human might not have failed over here. And we touched various applications varying from healthcare to Gmail responses to better farming. At one point we said that this is all good, but there are a lot of challenges also. For example, if you rely on self-driving cars and you properly don't understand what technology they are they completely autonomous driving, are they assistive driving? There can be certain accidents. We also saw about this bias in machine learning, where certain gender neutral languages get wrongly translated, creating some biases. Although they have been addressed, many of such systems have been now addressed. We also saw machine learning can be racist at times, and it can also look for the most common signal in the data. For example, in this signal, the bride to the left hand side might always be predicted to be the bride, because a lot of the brides in the data set are the western brides and not the eastern brides. We looked at some scary examples where in this video Barack Obama was speaking something which was artificially fed as a video, so he didn't actually speak all those things, and the poll season is now up to us, so now upon us, so we need to be very careful with such technologies. We discussed the roles of adversaries. Finally, we defined machine learning via 2 definitions. One, the simpler one, which is giving the computers the ability to learn without explicit programming, and the second one being learning from experience, E on a specific task, T with respect to performance measure, P. So both these definitions are commonly used. We looked at this specific point, giving the computers the ability to learn without being explicitly programmed. So we said that, let's say if you want to do some explicit programming to figure out what this particular character is it 1, 2, 3, 4 and on, we may come up with a set of rules. A 4 is a number which has a vertical line, another vertical line, a horizontal line joining those vertical lines, and another vertical line which extends below this. But we then discussed that if you had to write this this code in your favorite programming language, it will fail for a lot of cases. You may have one 4 written in this way, some other 4 written in some other way. So rather what we said is that we will instead use machine learning, and we looked at these 2 different paradigms. Traditional programming, where you hand write the code, you have data and you write the rules, which traditional programming will then help you to give the answers. Whereas in machine learning, we change the paradigm. We bring the answers to the left hand side, data and answers, machine learning gives you the set of rules. So this specific case seems like supervised learning. We also then said that let's do this grocery or tomato quality prediction. We have to firstly identify a set of features which could be useful for the task. We discussed that sample number is unlikely to be a good feature, but if the sample number is highly correlated with the batch or the truck, or in some sense is telling you the age of the fruit or the vegetable, it can be useful. So we created this problem where we divided the data set into training and testing, where the training set contains a matrix X containing few records, some number of records, and corresponding to each you have features, and then you have the labels or the output response variable. So therefore we came up with this convention. Your training of feature matrix is n cross p, n rows p dimensional each, and each example you can write as some p dimensional vector, and the output is an n dimensional vector. So this is for the case you have a single output, but you can also have multiple outputs. So therefore the machine learning task, in this case supervised learning task, becomes given this original training data set, learn the set of rules which when applied to the data with unknown condition or unknown output you can predict based on those set of rules. We then also looked at similar problem, but in the case of regression. In the case of classification, we are predicting k discrete classes, c discrete classes. In regression, we are predicting a continuous number. So classification could be classify an email as spam or not, tell whether or not someone will pass the course, or in the case of regression, we may have predict the energy consumption of this class, predict the amount of the price of a certain stock. So all those are real quantities, and we call those problems as regression tasks. So we then said that before we go on and learn machine learning methods, it might be important to first consider what is a good method. How do we quantify whether the method is working well or not? For that, we said that we typically consider a vector y hat of predictions and a vector y of our ground truth. So ground truth is collected by the system which is giving you the correct information. So then we looked at few metrics like accuracy, which tells the instances where both of them match with respect to the total number of instances. We also looked at the reasons why accuracy might be a very poor metric, such as imbalanced classes. So therefore we also said that let's look at some other metric like precision and recall. So the way I remember precision, I recommend everyone remember precision, is that you make a prediction and then check how precise your predictions are. How many times when you predicted the positive class did you actually have positive class in the ground truth? How precise were you in predicting the positive class? Recall is the other metric. Again, just remember the English definition. How many of the true labels, of the labels which were actually the positive class, am I able to recall in my predictions? So therefore for this, you look at all the examples where you have where you have the ground truth positive, which is first row, second row, and the last row, and you see how many of them are we predicting to be actually positive. We also said that we can encode all of this information via a confusion matrix which consists of true positive, true negative, false positive, false negatives, and we wrote precision and recall in terms of those quantities. We also calculated another coefficient called Matthews correlation coefficient, which works particularly better than the other metrics when the data is imbalanced. We also said you can do a multi-class confusion matrix. For regression, we said that the typically used metrics are mean squared error. Why do we not use mean error as a metric in regression tasks? Because it can get cancelled out. The errors can get cancelled out. You can make a plus 10 error and a minus 10 error. The overall error becomes 0, which is wrong. So therefore, we typically use mean squared error. I have also always suggested, if you want to remember such things, you start with from the right hand side and go to the left. First you find out the error, which is yi hat minus yi. You square the error, yi hat minus yi square, and then you calculate the mean over it, over the n examples. And then for root mean square error, you put a root over that. We also looked at mean absolute error. Find the error, take the absolute value of the error, take the mean. We then went on to the first algorithm, decision trees. One of the reasons we typically use decision trees is their simplicity, their ability to be easily interpreted, their ability to be programmed, and they serve as very good baseline methods, and when they're combined by ensemble learning, they become very powerful. So we considered 4 different cases: discrete input, discrete output, discrete input, real output, real input, real output, real input, discrete output. So we took this specific example, 14 examples, 14 samples data, where the problem was to predict yes and no. What we said is that if we consider the case, so we first saw this particular tree which was being drawn from this data set, and we observed that if the outlook is overcast, we play yes. So in essence, what we are trying to do in this algorithm is that we are trying to reduce the confusion which is in the examples. So if I look at the 14 examples as of now, I have 9 yes and 5 no's, which means I am a little confused. If I had 7 yeses and 7 no's, I would be more confused. If I had 14 yeses or 14 no's, I am not confused. So therefore, we came up with this definition of confusion, or the definition of impurity, which is known as entropy in this case. So our goal is to then divide or construct the tree in such a manner that the entropy is reduced over time with the depth of the tree. So in this particular case, the entropy at the leaf nodes is 0. We also importantly said that the algorithm which is being used in decision trees is a greedy algorithm. So this is a very simple example of a greedy algorithm. The yellow car is following cars which are going at 80 kph, but it feels that there is a lot of empty space here. It takes a greedy decision which is not optimal. It gets blocked behind the truck. So what we said is that we want to choose greedily a node. If we split on that node, we get the highest performance gain. And for deriving the highest performance gain, we first need to derive impurity. For 2 class problems, we saw this is the plot of impurity where it is going to vary from 0 to 1. So we have seen this question many times where people, if I ask for multiple classes, people still feel that it's between 0 and 1. It's not. So it's normalized impurity which will be between 0 and 1. We then said that 9 yeses, 5 no's gives us some high amount of impurity. But if we do a split on a particular attribute A given by this formula, which is information gain, you find out the entropy of S, and then you look at all the sub branches and find out their weighted entropies. So the difference between the entropy of the overall set minus the weighted entropies after split is your information gain. The algorithm was a simple algorithm. You start with the root, you label all the examples. If all of the examples of one particular class, you label that root with the label of that class. Otherwise, it's a recursive algorithm where you first find out the most important attribute as per information gain. You set that as root, and then for each value you recursively call this. You add a branch and you recursively call this on the subset of new examples. We also said that the depth of the tree is an important hyperparameter. So if we don't limit the depth of the tree, what is the training accuracy that you can get? You can get 100%. So the other thing which we also discussed about the decision tree algorithm towards the third, like let's say in the last quarter of the course, was that decision trees are non-parametric methods. They're non-parametric because as the data becomes more sophisticated, the tree can also become more sophisticated. One such symptom of the model becoming more complex is the actual number of nodes or the depth of the tree. So therefore, we typically want to limit the depth of the tree because if the model gets very complicated, it exhibits one of the 2 problems. One is bias, the other is variance. What problem does it exhibit? High variance. We looked at other variants of this where we are looking at minutes played, etc. Now there we have to use something like mean squared error as a notion of impurity. All of the other things will remain roughly the same. We looked at these set of examples also, which helps us understand the bias variance trade-off very nicely. If I have a depth of the tree as 1, then the model is clearly underfitting, exhibiting high bias. As I increase the depth, you can see that the model keeps getting better. But then after a while, you can notice that it starts overfitting to the data. Like this particular blue point should perhaps have been just predicted to be the red class. But because the model is very complex, like it can grow arbitrarily complex with respect to the data, therefore it can also highly overfit. We also looked at this interesting case of real input, real output, which is just decision trees used for regression, where we said that if you go beyond 6, your prediction is going to be what? 6. Go on the other side of 1, your prediction is going to be 0. So here also the idea is the same. You split the data into smaller subspaces, and on each of the smaller subspaces you call the same algorithm. And in decision tree for regression, you learn constant lines. So constant lines at some particular y value. Like even for the sine-like function, we will not be perfectly learning the sine function, but we will be learning different lines, different levels. We also looked at this this discussion on if the samples are weighted. Can anyone remind me, why do we need samples which are weighted in decision trees? Why did we need the different weights for samples in a decision tree? Sorry? Some features may have more importance. No, here we are not talking about the importance of the features. We are talking about the importance of different points. Yeah, so we looked at them in ensemble learning. That is what I was looking for. That we can use what methods? Boosting methods or bagging method, or like which kinds of methods will you use? Boosting like methods we discussed. You start with a simple model, and then you incrementally make it more complicated by looking at the samples it misclassified. So we discussed weighted entropy. Then we also discussed the bias variance. We are just looking at bias variance again. If we learn a tree of depth 1, it seems to be a good fit. But if instead we learned a tree with no depth limit, you can see that its tree depth 1 is a very simple tree. Tree of no depth limit is a very sophisticated tree, which is clearly exhibiting that it's a high bias model. And you can also see that over here, that it's learning to overfit to the data. So these particular blue points should not have been blue. So we also saw that high bias also means underfitting. Your model is not sophisticated enough to learn all the intricacies of the required data set. So for example, it's not able to learn that you should have another separating line here. This typically occurs when the depth of the tree is low. Overfitting is then when it is learning to the very specifics and the nuances of the data set, while it is forgetting the overall trend. And the other notion of variance is that it is showing that if you modify the data set even a little bit, the learnt model that you get is going to be very different from the other model. So therefore, even slight perturbation gives you a very different model. So overfitting is then equivalent to high variance. Now we can draw these curves for the accuracy that we get on the training data set and the test data set. So as we've discussed, for decision trees, as we increase the depth of the tree, the accuracy will only improve, because it's a very sophisticated model. You should be able to learn everything, but the test accuracy starts going up and then it starts becoming worse. So therefore, what we said is that we want to choose a region where the model exhibits a good fit, shown in this purple color. But importantly, we have always discussed in this course, we cannot use the test data to make this decision. Can anyone remind me why? Why don't we use the test set to make this decision about what depth or what hyperparameter to choose? We never have access to the test data set, as simple as that. So therefore, if we have to find the optimal depth of the decision tree, we typically use cross-validation. If we don't use cross-validation, we have a training data. We train a model on that. The learned model is then used to make the predictions on the test data, and then we calculate the error matrix. But this shows at least two problems. One, we are focusing only on one part of the data set as the test data. Maybe there is some bias in the train test split. So therefore, what people typically use is to use k-fold cross-validation, which means you divide your data set into multiple folds of train and test combinations. Through this way, each point in the data set is used at least once, exactly once in this case, as a test point. So typically when we look at cross validation, we divide the training data into train and validation. We train on the trained data, and with different hyperparameters, we train different models. We test those models on the validation data. We figure out which of them gives you the best hyperparameter. Once you learn that, you use those set of hyperparameters on the test data. The model learned on those hyperparameters on the test data. We also looked at nested cross validation. I'll just skip that for now. So post this exercise, we then went on to how to make our models better. Like we looked at decision trees. They typically don't give you very good performance. They're good baseline methods, but they don't give you very good performance. Instead, what people typically use is ensemble methods, where you're trying to combine the predictions from multiple models. We set the specific example of Kaun Banega Crorepati, who wants to be a millionaire. If the audience is asked some question, none of them may be treated as an expert, but largely they will be able to give the correct answer. So similarly, we looked at 3 different intuitions as to why ensemble methods may make sense. If the data is less, you can have competing hypotheses. You can also look at the fact that you're using greedy algorithms, you can get stuck in local optimas. And you also looked at that some classifiers and regressors cannot learn some complex representation. So as an example, if you have a decision tree of depth 1, you'll only be able to learn like axis parallel boundary, a single axis parallel boundary. Whereas, so we see that in this example, depth 1 tree will only learn an axis parallel boundary. It will not be able to see that we have this conical shape, which random forests are somehow able to do. We also stumbled upon this very important question, that if more models are always working, so if we add more models, if it always helps, we should just have infinite models. But then we discussed that there are certain conditions which tell us when a model works and when it doesn't work. As an example, so some specific conditions we looked at were each member has to be better than random accuracy, give you better than random accuracy, and you need to have some amount of diversity. You can't have each of the model give you the same prediction. So they have to make different errors on different data points. We also did some calculation from quantitative perspective. If we have 3 models with an error probability of 0.3, then the probability of ensemble being wrong is 0.19, which is less than 0.3. But we discussed that one of the most important conditions which you need to consider here is that the 3 models have to be independent of each other, which is rarely the case. So therefore, you typically don't go from 0.3 to 0.2, you'll probably go from 0.3 to 0.25 or 0.26. We looked at two variants. The first is bagging of ensemble methods, the other is boosting. So bagging is also known as bootstrap aggregation. Now we are trying to reduce 2 kinds of problems. The first is reduce the bias, the second is to reduce the variance. So in this bagging, we are trying to reduce the variance. The key idea is that you divide the data set using sampling with replacement. So I hope that now if I ask this question in the end semester, people get this correct. Okay, good, everyone woke up. Everyone went from look down to look up. Okay, I won't repeat the question, I'll edit it out from the recording. The question was, if I ask the effective size of a bagging round or bagging samples, will you be able to get the exact derivation correct this time? So what we do is we have a data set of size n, we create a new data set of size n with uniform sampling with replacement. So therefore we can have in each of the round, we can have some repetitions of samples. And we looked at this example. If we had this data set, so there are 2 anomalous points. But if we did sampling if we did not do sampling with replacement, we will get a fit like this, which is clearly exhibiting high variance. But if we did bagging with 5 rounds, in the first round we get a smaller data set, there are some samples which are repeated. So if we look at the 5 rounds and then we learn a classifier with no depth control on these, we get these 5 classifiers, and now we see if we were to test on this point, we will get a blue prediction, because in 3 out of the 5 trees that I created, of the bagging rounds that I had created, my learned prediction for this point here is blue. Similarly, for this point, 2 of my trees out of 5 are giving the wrong prediction, otherwise I am getting correct prediction. So basically, in summary, we say that we take strong learners, which are learners which exhibit a high amount of variance. We don't reduce the variance directly of the individual learner, but we create multiple such strong learners, assume them to be largely independent of each other, and then train on them and then combine them. Whereas the other algorithm, which is known as boosting, will start off with, it has to reduce the bias. So therefore, we have to look at models which exhibit high bias. These are models which are also known as weak learners. So weak learners, we will be combining them to reduce the bias. We incrementally build them, which is an important distinction between the bagging and boosting. In bagging, we can have parallel rounds. Like each classifier that we build or each model that we build is completely independently built of the other model. Not completely independent, but completely independently built. Whereas in boosting, we start off with a base model. We look at the simple base model and we see where it's making errors, misclassified points. And our main algorithm is to increase the weight of the misclassified samples, decrease the weight of the correctly classified samples, and then build a new model on top of that with the new weighted set of samples. So we saw that these 3 points are misclassified. In the next iteration, their weights are increased to 0.15, and the samples which are correctly classified, their weights become 0.06. Our overall objective becomes to reduce the weighted error or the overall error with different samples having different weights. On repeating this further, we look at multiple such trees, multiple such predictors with different alpha values, which acts as a weight for these models. We typically see that as we increase the iterations, the weight increases, giving more importance to the tree which are built more later, to the models which are built more later. Finally, we look at the prediction from each of these, but weigh those predictions by the alpha values. We also discuss this feature importance, how we can get a feature importance. In Crux, we look at from random forest. In Crux, we say that we look at a specific node and where it occurs in the M trees that I've created. If a node occurs at the top across all the trees, it is likely to be a very important node, because it is giving you a lot of information gain across the different trees. And these different trees are also highly decorrelated just because of the way we construct them. So the important distinction between just other methods and random forests is that each time you have to make this decision of which features to choose, you always use a subset of the total set of features. This gives you highly decorrelated trees. One benefit of highly decorrelated trees is that your models become independent of each other, which means in symbol learning, the quantitative discussion that we are having is more likely to work better. Okay, random forest we have discussed. Then we started the discussion on linear regression. That's where we really started having some maths. Before that, it was some very simple naive algorithms in some sense. We discussed that we will create expressions of the form of, like we looked at this demand of water in the campus. We can say that it's some base demand plus some positive constant into the number of occupants plus some other positive constant into the temperature that we have. So we similarly write for the case of linear regression that we'd have for prediction for n examples as a vector y1 hat till yn hat, our feature matrix as the first column of ones and then the original features, capital M features for each example, and we can say that yi hat, this y hat vector is this x vector times the theta vector. The theta vector is indicating the parameters of a model. Now we said this is linear regression because of the fact that these equations are linear in the parameters, not linear in the data. So we mainly write this equation as y hat equal to x theta. Then our objective is to find out the theta. That's the learning task here. Theta is a set of parameters. We visually looked at what we need. So we say that yi equal to yi hat plus epsilon I. We forget about the distribution for now. So our overall objective is to minimize the errors between our prediction and the ground truth values. We say that that can be if errors are epsilon 1, epsilon 2, epsilon 3. One way to encode that is the magnitudes of each of them should be small, or the other is that we minimize summation epsilon I squared, or the L2 norm of the epsilon vector or the L1 norm of the epsilon vector. So there are different combinations. We then wrote this in vectorial form, y equal to x theta plus the epsilon vector. Y is a vector, epsilon is a vector, x theta has to be a vector. So y theta is mainly the y hat vector. And then if we want to learn theta, we can say that, so we write epsilon to be y minus x theta, and epsilon transpose epsilon we can write in this expression. So we look at our overall objective, which is epsilon transpose epsilon. We minimize that with respect to theta, set it to 0. We do a bit of vector calculus and we get theta hat equal to x transpose x inverse times x transpose y. We looked at a few examples for this calculation. Then we also discussed the same question that we are discussing about linearity, but linearity in the parameters. So if we look at these 5 examples, barring the last example, all of them are linear models, will fit with linear regression because they are linear in the parameters. The last one is not linear in parameters, it's exponential in the parameters. Whereas when we can create these additional features, t squared, t cube, cos of something, these are just feature transformations, or also called the basis expansion. So we looked at a few basis functions like the polynomial basis, 1x, x squared, x cube, Fourier basis, 1 sin x, cos x, then different frequencies of sines. Gaussian basis is the same as what we've also seen in the RBF kernel. Sigmoid basis is another simple basis. We also discussed the geometric interpretation of least squares or of linear regression. So we did a bunch of things, but essentially what we wanted to say is that you are trying to seek your y hat. Let me see, right. Your y hat always has to lie in this x theta space, right. So therefore you are trying to choose a theta in such a way that the distance to the y vector shown in green and y hat vector shown in light green is minimized. That happens when y and y hat vector will be perpendicular to each other. So therefore we say y minus y hat is perpendicular to xj's, where xj's are lying in this space. So we then also can write this as x transpose into y minus x theta equal to 0, or we again get the same expression, theta hat equal to x transpose x inverse x transpose y. With this particular formulation, we discussed a few problems, specifically when x transpose x, the inverse of it is not computable. This is also typically known as multi-collinearity. So one of the feature is dependent on the other feature. So we also looked at some ways to address this problem. One was to do regularization, which means you add something to the diagonals so that the system is not low rank, and drop some variables, and we could also additionally avoid the dummy variable trap. So in the dummy variable trap, we said is that we have to encode categorical variables, but we need to encode them in a very particular fashion. Like if I am trying to model the pollution with respect to the wind speed, wind direction vehicles, wind direction is a categorical feature. but we do not encode north 0, east 1, west 2, south 3, because this forces the pollution in south to be always more than north or always less than north. We have introduced some notion of order here which does not exist. So we also discussed that typically what we use is n-1 variable encoding. So if we ask 3 questions, n-1 questions, and then for the south category we just put 0, 0, 0. But if we used n variable encoding, we'll instead of asking n-1 questions, you'll ask n questions. And if you feed that additional features into your matrix, you will end up creating this situation where is it south is always, we know that 1 minus the sum of the other columns. So therefore this will lead to multicollinearity. Okay, this lecture went longer. I have discussed the entire lecture. We then said that one particular method of learning the theta parameters was the normal equation, but it typically gives you a lot of problems in terms of how to solve and how to, and especially if the matrices are pretty long, are pretty big. So therefore people typically use gradient descent, which is an iterative algorithm. We previously had looked at the notion of gradient and its relationship to contour plots. We said that if we want to minimize or maximize some function, we can then focus on gradient descent algorithm as such, which is mainly you initialize the parameters to some random value. You find the gradient of the cost function or the objective function at that particular theta, which is the gradient evaluated at the particular theta. And for each iteration, you do this gradient descent update rule, which is the new value of theta is the older value of theta minus alpha times the gradient evaluated at the previous value of theta. We had also done the derivation of the gradient descent from the Taylor series, and we said it's a first order method. So we looked at Taylor series as an expansion of any function or an approximation of any function as a polynomial expansion around that point x naught. And we had also looked at the multivariate case of that, and then we had derived the gradient descent update rule. I'll skip all of that. We then looked at some specific examples of gradient descent working, and we took a lot of examples for using the code. So here we can see that over the iterations the cost is going down and we are reaching the minimum, reaching close to the minimum of the objective function, and the line fit is correspondingly improving. Right. So we also at one point discussed that the shapes of these contours are ellipses, although I said that this is not going to come in the exam, but for interested people they can read through it. We then said that gradient descent is often not used because here also you are trying to make the updates for a theta after having looked at the entire data set, which makes it again very slow to change. The theta changes very slowly. Secondly, again you require a lot of memory because you have to look at the entire data set to make one update to the theta vector. Instead, the other variant is known as stochastic gradient descent. Here for each sample that you see, you update the value of theta. The in between one is mini batch gradient descent. You look at batches of data and update the value of theta. We also then looked at the difference between an epoch and an iteration. So epoch is each time you look at the entire data set. Iteration is when you update the value of theta. We looked at different examples of SGD versus gradient descent. Then we looked at this very important discussion on that the stochastic gradient is an unbiased estimator of the true gradient. So we said that we looked at this geometrically as well as through some simple calculus. So this is one of the reasons of the success of stochastic gradient descent, and therefore one of the reasons of the success of neural networks, that we can decompose the gradients over the individual points, which makes it an unbiased estimator. So in one of the lectures tutorials we had looked at the definition of biased and unbiased estimator. Oh, in this one also we had that in detail. We had also then studied the time complexity of gradient descent versus normal equation. So I'll not go over those details, but the important thing was we consider all the matrices, their different operations that we're doing. So find out the shape of X transpose D, find out the shape of X, look at the time complexity when you multiply a D cross N matrix with the N cross D matrix, find out the complexity of an inverse, which is cubic, find out the time complexity of X transpose into Y and this of this product. We then collected some data from you on movie recommendation. So we said that the idea is that once you have this matrix of users and movies with a lot of missing entries, you want to fill out those missing entries. And we posed this as a matrix factorization problem, which is to say that this entire movie, user movie matrix, I will say that it can be expressed as a product of two matrices. One is the user matrix, the other is the movie matrix. So we also looked at why we can do that, because we assume that each movie can be represented using a small set of features. So it's therefore we can learn a low rank representation, low dimensional representation of a movie. Similarly, for each user, we can learn the affinity towards each of these factors. So therefore it's a low rank decomposition. We generally write this as the matrix A n cross M can be approximated with the product of two matrices W and H, n cross R and R cross M. R is the rank and of the reduced decomposition. It's significantly lower than N and M. We said that there are various ways in which, two ways primary in which you can learn these values of W and H. One is you minimize the Frobenius norm of A minus WH, square of the Frobenius norm over W and H. So then you can just use gradient descent directly, or you could use alternative least square, where I just showed how you can decompose this problem to something similar to what we discussed in the case of linear regression. So we do that column wise, and we're able to still, over a for loop, we're able to get in the least square form. At this point, we said that we have looked at linear regression, we have looked at some variants, we have looked at how it can be applied to non-trivial problems like movie recommendation. But one important thing which we want to do in linear regression like methods is to reduce the variance. So there are specific ways in which you can reduce the variance or overfitting. One method of understanding overfitting is that the coefficients, their magnitudes become very large. So because they're trying to just fit as well as possible to the data. So therefore, in cases like these, it was a very high degree curve that we're fitting. Some of the coefficients would be very positive, some of them would be very negative in order to accommodate all the training data points. So therefore, we said that if we want to prevent overfitting, one such method is to put penalties on large theta vectors, theta i's. And one way to do that is you can now minimize y minus x theta transpose y minus x theta subject to theta transpose theta less than a particular quantity. And now that you have studied SVMs, you can see that this is the primal form of minimize something with respect to something else. You can convert it to a dual form by rewriting y minus x theta transpose y minus x theta plus lambda times something. Once we do that, we use the KKT conditions to write it in this form, minimize y minus x theta transpose y minus x theta plus some non-negative constant times theta transpose theta. And then we find out that the ridge regression solution is almost similar to the linear regression solution, with the difference being that you have this mu times identity matrix in the inverse. We clearly see that if mu is very high, it will reduce the variance. If mu is very low, it will have high variance. We also looked at this other interpretation of regularization, where because you are adding mu's to the diagonal of x transpose x, so the matrix x transpose x plus mu I is likely to be always invertible. We then looked at the other variant, which is lasso regression. So lasso regression is pretty similar to ridge regression, but instead of the L2 norm, you have the L1 norm. penalty on the parameters theta. Post the mid-sem, we discussed logistic regression, which we can think of as the simplest neural network. While the name says regression, it is a classification problem, where we said that we want to predict the probability of your y being certain thing given the input features. So once we write probability of y equal to 1 given x as x theta in the same form as linear regression, we know that x theta is unbounded. It can be from minus infinity to infinity. So therefore, we cannot directly use probability of y equal to 1 given x as x transpose theta. So therefore, we need to bound it between 0 to 1. So therefore, we use this squashing function, which is the sigmoid function, which transforms it to be between 0 and 1. The interesting thing about the sigmoid function is that not only is it binding between 0 and 1, you can also see that in terms of the gradients, where do you expect to see the highest gradient in the sigmoid function? Around what values of z? Z equal to 0, you can see that you get the highest slope there. So this is one of the questions I often ask not in the quiz, so you don't need to wake up. I ask this in certain interviews that what is the maximum value of the gradient that you can get with the sigmoid function, and beyond certain ranges you can see that the gradients are always almost close to 0. So such neurons in neural networks are also called dead neurons, because the gradients they're saturated, the gradients are almost close to 0. Whereas with ReLU, we don't see this problem. So once we look at ReLU, the maximum gradient that you can also get it at this point. So you know the function, which is the gradient at any z is sigma z into 1 minus sigma z. At z equal to 0, sigma z is 0.5, 1 minus sigma z is 0.5. So therefore, the maximum gradient that you can get using the logistic function is 0.25. Whereas with ReLU, do you have any such limits? No. So we also wanted to find out the decision boundary. So we wrote p of y equal to 1 given x and p of y equal to 0 given x, and we simplified them to get our log odds equal to x theta. Logits is x theta. So therefore, whenever I discuss about the code, I said that we should always be just computing the logits. Directly pass the logits to the cost function. So decision boundary is x theta equal to 0, which is a linear decision boundary. For learning the parameters, we said that we do not use the squared loss function. It's not convex. Secondly, it does not put very high penalty on misclassifications. Instead, we don't look at this derivation, but I directly showed you the cross entropy loss function, which is minus yi log yi hat plus 1 minus yi log of 1 minus yi hat. We looked at the interpretation of that, then we looked at the derivation of the cross entropy loss and the gradient with respect to that. Then as we discuss feature transformation for linear regression, we can also do for logistic regression. Now this ties back to the recent lectures on SVM. So you can transform the feature space into a high dimension space where the data is linearly separable. So in this case, you have projected to x1 square, x2 square a high dimension space, and the circular boundary in the high dimensional space is actually linear in those features. We looked at multi-class prediction, where we can then use something like the softmax function instead of the sigmoid. It's a generalization of the sigmoid. And we've been asking this question in the exams. How do you prove that softmax for two classes is the sigmoid function? Post that, we started discussion on multi-layer perceptrons. So or on neural networks. We said that they are the state-of-the-art networks in most of the fields. And the typical paradigm has changed. So with the earlier models, you would start off with the inputs, you will extract out the features, you would then feed that to a classifier, which meant that the initial part of the pipeline was handcrafted features and the last part was the only trainable one. Whereas with neural networks, what we're saying is that we do end-to-end learning and we learn the lower level features, high level features, classify. We don't have to explicitly do some feature engineering. So we started looking at so we also looked at this, what is this called, TF playground, where we said that we can, so this is now a non-linear data. If I use sigmoid as a classifier and one hidden layer with one neuron, this is my logistic regression. If I have to train over this, I will always be able to learn a line, because the decision boundary in logistic regression is a line. Now, in order to fit this data well, I can introduce additional features and I am able to learn the perfect fit. But importantly, I had to do this feature engineering on my own. Instead, if I don't do any feature engineering and I just use a neural network, and I'll also change the activation to make it quicker. So then, without doing any feature engineering, I'm able to learn those low level features as a part of the pipeline, and I'm able to still do this learning. So the feature engineering, which can often be very expensive in terms of requiring the domain expertise, you are avoiding. Plus, you can do a lot more sophisticated things to get significantly better results. We started the discussion on perceptron. Now, if you look at the perceptrons, you may be again able to see how it keeps on repeating. Linear regression, we saw the perceptron summation wxi plus b. Logistic regression, we used the logits x theta. We had looked at it now from perceptron. We also looked at it in SVMs. So perceptrons for binary input, binary output. But then we also discussed how the perceptrons are very limited, because they cannot classify XOR-like data or the data where the data sets where the data is not linearly separable, until unless you project them to high dimensional space. Whereas many other models at this point of time were able to do this. So therefore, people moved on from the neural networks bandwagon to the other models. But then eventually people started using multi-layer perceptrons with some activation functions, and the backpropagation algorithm was rediscovered in this community. So we looked at a few different activation functions, and we also looked at the gradients. We then said we want activation functions to satisfy a few properties. They have to be non-linear, otherwise you will still learn a linear regression like model only. We discussed this in the quizzes also. And small change in input leads to small change in the output. We then defined multi-layer perceptrons to consist of the input layers, a few hidden layers. In the hidden layer, you have, in each such layer, you have two main kinds of computations. The first is computation of z, which is summation wi xi or theta I xi plus the bias b, and then the a, which is an activation or a thresholding of that. So we then came up with this terminology of what is an activation, what is z, what is a, what is the activation function g. And we looked at a few examples to understand this better, to get a sense of the shapes, to vectorize these. But more or less, we don't need to do this in practice, given that our neural network libraries are very powerful and they handle these cases. Look at the summary of shapes, and we solved the ReLU problem using XOR. Finally, we were able to solve. Perceptron was unable to solve. And then we looked at the computation for n examples and the number of parameters. It's a huge number of parameters in modern day neural networks we get using this formula, which is NL into NL minus 1 plus NL. This component is telling about the bias neurons in the Lth layer. This is the number of neurons in the L minus 1th layer and the number of neurons in the Lth layer. We said that if we have to learn the parameters, we have to do backprop. So forward prop moves from the inputs to give you the outputs. Backprop moves from the loss to give you the parameters which need to be updated to get better loss. So we just use gradient descent at this stage. We then looked at a very interesting specific application of multi-layer perceptrons, which is to generate the next token. We discussed a lot about GPT-like systems, and how one of the important pre-training tasks is to predict the next character, and then they are fine-tuned on specific tasks. So one more example I can give. So let's say if you have a chat GPT-like system, the pre-training would still be the same, that you predict the next token, and then let's say you have specified it on, you have fine-tuned it on some specific tasks. Now I can build a further fine-tuning which doesn't give me text output, but it's fine-tuned to just give me code. So whenever I give it a few examples, few short learning, few short fine-tuning, I will get a few examples of certain questions, certain answers in code. I give the code. So therefore, if I have to generate code, it will be better able to do that because it's been fine-tuned on that data set. This was also asked in one of your quizzes. I think I severely underestimated the amount of effort it takes to speak at this speed when about 20% of the audience is either busy in their assignments or busy in sleeping. But anyway, the next character prediction, we say that we pose as a classification task where we are trying to predict which one of the classes it is. In this case, it's lowercase characters. So we specifically looked at this problem of generating Indian names. The important thing which we said is that we will be able to do a representation learning through this, which if we said in 2 dimensions, we expect, let's say, the vowels to cluster together, the non-vowels to cluster together. And we also discuss other systems which have already done that, like word2vec, etc. So importantly, we have to create this embedding table, which is a lookup table. Given a new character, I want to look into this table and get this vector representation of that. So each of the 27 characters here, I can represent using some k-dimensional embedding or feature space, and this embedding space is also learnable. So once I look up a character from this table, I get some set of values. I concatenate them, I feed them into my multi-layer perceptrons. So therefore, such models have 2 kinds of parameters. One is the embedding table, which goes from a particular character to an embedding. The second is the parameter vectors, the parameters of this multi-layer perceptron. Post this, we looked at AutoGrad, which is the backbone engine behind automatic gradient computation, which makes neural network libraries very amenable for doing research these days. In the older days, people had to write the back propagation routines on their own, and oftentimes in C-like languages. So AutoGrad, we said, it is not finite differences. Finite differences could be one-sided, two-sided, which is just f of x plus h minus fx over h, or two-sided f of x plus h minus f of x minus h over 2h. We said that is very expensive because here the x, for our neural networks, these x's will be the different parameters, theta 1 till theta n. And we have to compute this for each individual theta parameter, we have to do a forward pass. Secondly, they are numerically unstable. So therefore, instead we say that we will use reverse mode autodiff, where we create a computational graph consisting of nodes and edges. For example, x into y plus z, we write it x and y as inputs, they are multiplied and then z is added. So this is a simple computation graph. Importantly, all of the thing boils down to in the computational graph methods of finding autodiff is if we consider a part of the graph where the 2 inputs are x and y and the output is z equal to some function of x and y, we can compute the gradient coming into the node, which is dj by dz, where j is some cost function. So this is known as the upstream gradient, and we also know the local gradients because f is a function of x and y. So we know what is the gradient with respect to x and y, which is known as the local gradient. So if we want to find the gradient of the loss with respect to x and y, we can compute it as the product of the upstream gradient dj by dz into the local gradient, which is dz by dy. So that's the crux of computational graphs. And we looked at one specific example, which is a logistic regression problem. We solved it end to end using scientific calculators and just using simple Python code, where we compute L given the inputs, then we compute del L by del L, which is 1. Then we look at L is minus 1 into F9. We say that with respect to this node, what is the local gradient, what is the upstream gradient, and we keep going from right to left. We solve this entire examples. At this point, we then discussed convolutional neural networks. One of the prime motivation behind using convolutional neural networks was they will work very well for image-like data, and they'll work well. One thing is that the modern MLPs are not going to work well for image-like data because they don't consider the spatial structure. The number of parameters in such multi-layer perceptrons will be huge, whereas the specific methods CNNs, they'll work well because they are focusing on building some feature detectors, let's say a cat ear detector, and they also try to preserve the spatial structure, and also if the feature occurs anywhere in the image, it is not a problem for such networks. We discussed the building blocks, which is the convolution operation of the filter, so the filter and the convolution operation. We also then considered the sizes of the different images after we apply the convolution operation. So we can also think of this convolution operation to be very efficient because we learn a filter which is multiplied or which is applied across the entire image. So it's in some sense you are sharing the parameters across the different parts of the image, whereas if we just use a multi-layer perceptron, for each specific subpart of the image you have a different network, different set of parameters theta. But here you have a single filter which is working across the entire image. We then discussed about a few problems where we need to increase the size, where each image is not getting the correct enough representation. So therefore we looked at strides and padding and pooling to subsampling. And then we discussed if we have multiple channels, then how do we do the CNN learning, or how do we get the forward prediction to get the overall output. We looked at specific variants like LayNet, and we looked at an exercise where we were trying to compute the different parameters of the models and their shapes and sizes. And we also discussed that LayNet 5 is not very different from AlexNet, which was the winning model for the ImageNet challenge in 2012, I think. So therefore it was down to three things primarily. One was better compute, better data, and what is the third thing? Better algorithms. Like different activations were proposed, different kinds of methods to backpropagation were proposed, different model initializations were proposed. After CNNs, we went and discussed k-nearest neighbors. Okay, the page is not found. I think I'd uploaded it. But anyway, so in KNNs we discussed that it's a non-parametric algorithm. The complexity will grow with respect to the amount of data that you can give. Secondly, with KNN, it's a lazy algorithm. There is no step at the training stage. You only have to do computation at the test stage. The algorithm is relatively simple. You find out at test time what are my closest k neighbors from the training data set, and then you just do some aggregation over that. But we computed the time complexity and told that it's very, very complicated because it's linear in the number of samples, and therefore if you have millions of training examples, such an algorithm will be very slow. So therefore instead we looked at a few approximate KNN algorithms, where the idea was that can you do something at the training stage so that the amount of computation required at the test stage is reduced. So the key idea was that we break down the entire subspace in the entire space into smaller subspaces, and then you do this lookup, this exhaustive search over a smaller subspace. We looked at two kinds of methods. The first one is the KD tree, where you divide the total subspaces using k-dimensional trees, which is axis parallel splits we do. And finally, when we want to make a prediction, we just look at the specific sub-region in which your test data point lies. In contrast, we looked at the other method, which is locality sensitive hashing with random projections, where instead of axis parallel splits, we do random splits. And there also for each split, we assign a bit to this hash code, and then for example for this sub-region we have the hash code 00. So then again, if I have a test point over here, I need to just look at the sub-regions or the set of points where the hash code is 0, 0. So finishing the KNN, we then also discussed about reinforcement learning, which is a very different kind of a paradigm as compared to the supervised and unsupervised learning. We started off with the example of the Flappy Bird. We looked at a code which actually worked, and you also saw how horrible I was, and therefore I changed the code to the game where I was able to work. I see a lot of people nodding their head, so I was truly horrible in playing the game. We looked at a few things. One is, when we play such games, we get a score. Our objective is to maximize our score. We have a few actions we can take. In this case, you tap or you don't tap. And there is an environment in which you're playing. Your agent is this bird. There is an environment where the agent is playing. So the environment will provide a few things, a reward, not necessarily the score. For example, for each second that you're alive in the game, maybe the environment gives you a reward of +1. For each set of pipes that you pass, maybe the environment gives you a score of +1, something like that. So in that way, you can see that the score and reward can be decoupled. It also gives us some observations, let's say the pixel level information, and we have to then look at those observations and process them into a state. Let's say the state in this case is just the 3 relevant things. Like, we don't really care about the buildings or the clouds, the distance from the ground, the horizontal distance to the pipes, and the gap between the bottom pipe and the upper pipe. So you can think of, in this case, the state as a subset or processed form of the information in the observation space. We also discussed this block diagram between the agent and the environment. The agent carries out an action AT, it gives it to the environment will give back some observations which are then processed into some new state, and the environment also gives you a reward. We looked at the OpenAI Gym environment, one specific example of the mountain car, where there were a specific set of rewards, and we said that overall objective is to maximize the total reward. Often we do a discounted reward because in future we do some weighing factor, we want to give more reward to the present. So therefore we have this gamma weighing factor, which is between 0 and 1, which is the power of gamma is multiplied with gamma raised to power t is multiplied with the RT. And we then came on to the Q function, which tells you how much, if you want to choose an action, what is the total reward that you can get from expected reward that you can get from a particular state. We looked at a simple example of a Q table. It's a mapping from states to different actions. So in the discrete states and discrete actions, for each state action pair, you can get these values. Your objective is to learn such values from the data set. And then once you've learned, from the simulator, from the problem, once you've learned these, then what you do is to, given a particular state, you choose the action which maximizes the Q value. So it's in that sense a local, it's a greedy approach that you take. Then we discussed that the states in many cases are not discrete. They can be in continuous space, so you can discretize those and then put them in the table. And then with respect to the discrete state, we looked at the update rule with discretization. And then we looked at the Bellman equation, which is the recursive relationship between Q of S comma A. And then if you go from state A after having taken action A, you go to state S dash, and then in S dash you see the same thing. Like, you want to define Q as the expected reward, you write that as the expected reward you get after taking action A from state S, and then you go to state A dash. So you multiply that with gamma and maximize, choose the maximum A dash, choose the action which maximizes this. So it's a recursive relationship, and the update rule is, therefore from this recursive relationship we are able to come up with the updated rule. We looked at a few notebooks for this. After that, thus far we had been discussing supervised learning, and recently we just discussed reinforcement learning. But the other paradigm is the unsupervised learning, where we say that we are just given the X's, the input features, we are not given the output features. So we are trying to learn some structure in the data. One such popular class of problems is known as clustering. So for example, given these power profiles across 1000 homes, we are trying to see various clusters, we can see that almost everyone sleeps during these and their electricity consumption is low, but that maybe during 8 a.m. there are few people who leave the home, and so therefore we can identify 2 or 3 different clusters. So we can then ask the electricity board to reach out to these people with different offers. So that's the utility of clustering. You can see these 3 different clusters. We also saw other kinds of problems like dimensionality reduction. You did PC in one of the assignments. We also saw how you can, through dimensionality reduction, you can visualize high dimensional inputs into a 2D space, very useful. We also looked at matrix completion. There are other graph structures, etc. In clustering, we looked at 2 algorithms, the first being k-means, the second being hierarchical clustering. In k-means, you have to pre-specify the number of clusters k, and in hierarchical, you don't do that. So the important thing which we said is that a good clustering is that when the variation within the cluster is a small number. So we then just specified it using some notation, and we saw a few examples of k-means in action. Hierarchical clustering, we learn, given this kind of a data set, we learn a dendrogram. This thing is known as a dendrogram. Now in this dendrogram, if I cut the dendrogram at different places, it tells me the different clustering possibles. So if I cut it at the something above 60, I get 0 cluster, everything is in one cluster. If I cut it over here, I get 2 clusters, and so on and so forth. Like these 2 clusters would be this set of points and this set of points. So you can further break it down using vertical cuts. Now, finally to SVMs. So support vector machines, we have been revising this also. It's a very popular binary classification technique. We said that we want to maximize the margin, separating the 2 classes of points. And if you have to specify the margin or maximize the margin, we have to mathematically write it, which comes in the form of, so we are able to write the margin mathematically. Before that, we can write a hyperplane, and margin is the gap between the 2 hyperplanes. So the margin we end up writing as some as 1 over the magnitude of the W vector. We have specifically written 2 here given the convention of Wx plus b equal to -1 and Wx plus b equal to +1. So there the margin is 2 over the magnitude of the W vector. So our goal is to maximize the margin or minimize the magnitude of W vector such that we correctly label all the points. The labeling of all the points, we say we can write with respect to the inequality of yi into W dot x plus b is greater than or equal to 1. xi plus p greater than or equal to 1, which is a primal formulation. We looked at a specific example in 1D for the primal formulation via the different inequalities, and we looked at the feasible region as the intersection of these different inequalities regions, and we found out that 2 of these inequalities are binding in nature. So these correspond to the support vectors, which are the points which lie on the margin. We then moved from the primal form to the dual form, where we introduce an alpha multiplier for each of the inequality, and then we did a bit of calculations, and most importantly we wrote this y hat of x test equal to sine of W dot x test plus b. In the dual we write it as alpha I yj xi dot x test. So then we moved on to the case where the data is non-linearly separable. So we said that we can project the data to a high dimensional space. We did all those discussions. Instead, we said that this high dimensional space is like phi of xi dot phi of xj. We replace this phi xi dot phi xj because it's very expensive, in certain cases cannot be computed, with a kernel function. So we looked at a few kernel examples, kernel function examples, and the subspace in which they lie. And we also looked at the RBF kernel. The important thing of the kernel functions is that for each, they have dot products in the lower dimensional space. So we then in the previous lecture looked at the other variant, which is soft margin SVM, when we can introduce a notion of slack. So we are okay with slight misclassifications, and we said that there are 3 categories of misclassifications, 2 categories of misclassifications. One is the points which are like this small red point, which is on the correct side of the separating hyperplane, but on the wrong side of the margin. The second is this red point, which is on the wrong side of the separating hyperplane itself. So it is wrongly classified. And we say that we are okay with introducing a parameter penalty of epsilon I corresponding to how far we are away from the correct margin. So we then finally change the objective to the previous objective plus C times the sum of the slack, sum of the penalties for the individual points. And then correspondingly in the dual, we can also write this. We discuss the bias variance trade-off with respect to the parameter C. If C is tending to infinity, we get the hard margin SVM because we don't want any slack. If C is a small value, we will get a very high bias because this point will be now misclassified. With C being higher, all the points are likely to be correctly classified, but the margin is so thin that you can get, even one point is shifted left or right, you'll get a wrong prediction. So we then finally said that we can write this loss also in the loss plus penalty form, this SVM loss, which is known as the hinge loss. We discussed the hinge is like analogous to the hinge you have in the doors. So you can write some hinge loss plus some regularization. So with this, I'll